All right, in this screencast, I'm going to work through the worksheet that's due on Tuesday with you and help you understand how to figure out what the elastic potential energy is that's held in a spring from a graph of the force versus displacement. So this is the first problem on that worksheet. So let me relocate this a little bit. All right. So let's suppose a lab group found that there's a mathematical model of a force versus displacement of a spring that had this form. The slope of that, if you haven't noticed yet, I hope you have on your worksheet that you did for the PHET lab, that slope of a force versus displacement graph for the spring is the same as the spring constant. So this is the spring constant K. So Hooke's law is the force of a spring is negative K times delta X. The negative being that the spring force is opposite the direction of the displacement. So if you extend a spring, if you pull a spring and cause it to stretch, the spring is pulling back the other way. So you're displacing the spring, let's say to the right, you're pulling a horizontal spring to the right, it's going to want to pull back the spring force to the left. So that's why you have a negative sign in there. That's what that's doing. All right, but K is the slope. So it's very easy to graph this. And you have graphically determine the amount of energy as part one. Well, first we have to create the graph, all right? So, and they ask you to put the maximum displacement at 0.25. So if I put the maximum displacement at 0.25 and this is 0, I think I can just put everything on this scale at 0.05 meters or 5 centimeters. And this is X in meters. F in newtons. Now, if the slope is 1,000, that means this is going to be 5 newtons. This is going to be 10 newtons. This is going to be 15, 20, and 25. And this is going to be a very linear graph. Okay, so that you should be able to put that graph together pretty easily. All I did was I substituted in 0.1, for example, into this equation up here and got my 10 newtons. So I can very easily find those points on the graph, and now I've got a graph of force versus displacement. Well, now how do I use this graph now? You should have had a similar graph from your lab on Friday, but how do I use this graph to determine the amount of energy stored in the spring? Well, let's think about this. And I'm stretching the spring from 0 to 10 centimeters. So I'm going from here to here on my graph, and I want to know how much energy is stored. Well, the two things that we have traditionally looked at a graph for are slopes and area. Well, we already know the slope of this graph is defined as the spring constant K. What about the area of this graph? Well, does it make sense that the more I stretch or compress a spring, the more energy is stored in it? In other words, let's say I compress the spring a little bit and I put a ball on top of it and I let it go. The ball is going to be pushed upwards if the spring is vertical, let's say, on a table, and I push it down a little bit, the ball is going to spring upwards. But if I push it down more, the more I compress it, the higher the ball is going to go. So it seems like, yeah, the more I compress a spring, the more energy is stored in it. Well, the more I compress a spring here, if I were to go up my graph, you can see the area under the graph is increasing. So it makes sense that maybe the area represents that energy. And in fact, it does. So we're going to say this area of this graph right here, from 0 to 10 centimeters, if we can find the area of that little triangle, that's going to be the amount of energy stored in the spring. Well, area of a triangle is 1/2 base times height. So I'm going to call this Your textbook uses potential energy. It uses a symbol U, and I think it uses an S for spring. So potential energy in a spring object, or it might be an E for elastic. I believe it's an S though. So US equals 1/2. The base in this case is time. Is displacement delta x, and the height. This is the height, is the force. Okay, so all I have to do is find 1/2 delta x times F. But I'm going to do a substitution step here because I know in Hooke's law, the magnitude, I'm going to ignore the minus sign because I don't care what direction the force is. The magnitude of the force is equal to the spring constant times delta x. So I could substitute K times delta x in for that force of the spring. And I would get US is equal to 1/2, equals to 1/2 delta x times K delta x. That's what I substituted in for the force. I can multiply delta x by itself, and it's just delta x squared. So here is your equation for elastic or spring potential energy. 1/2 the spring constant times the stretch. This is the amount of stretch or compression. It's not the length of the spring, it's the stretch or the compression of the spring, which is what's on the x-axis here. That's the amount that the spring has been stretched, displaced. Okay, so that's easy to do. It's the K value here is 1,000. The delta x is, the base is 0.1. So 0.1 squared times 1,000. I'll let you guys do the math. And that's the answer to part A. The second part is the amount of energy stored when the spring goes from 0.15 to 0.25. Keep in mind that it's starting already at this point right here, and it's going to this point right here. So it's going to be the area under this graph from this point to this point. So be careful about the area formula you use for that. Okay? All right, so that is how you do number 1. Problem number 2, I think you guys, problem 2 here, you guys should be okay with. There's nothing unusual here. You can determine the spring constant of the spring for both of these cases based on the feature of the graph that you should know by now represents the spring constant. And so all of these are just interpreting this graph. Notice that this worksheet does not go with our textbook, so this is US. So E elastic is elastic energy. That's the same as elastic potential energy, or US in our lingo. Energy is measured in joules. I should have mentioned that up above. So the units of energy, let's go back to this. 1/2 K delta x squared is a Newton, per meter is a K, and this is meters squared. So I get a Newton times a meter for units of energy, because I have square meters from my delta x in my equation up above. My K value is in newtons per meter. That's the units of spring constant. So when I combine those together, I multiply newtons over meters by meters squared. One of these cancels out, and that's what I'm left with, newtons times meter. That is also called a joule, named after James Joule from chemistry last year. If you did any work with calories or anything like that, energy units in the SI system are joules, capital J. It's the same for mechanical energy in physics as chemical energy that you're used to from chemistry, only we're going to talk about different types of energy in physics than you're used to in chemistry. Okay, so these are equivalent. A Newton times a meter and a joule are the same thing. Okay? That's all for today. I hope you can do that worksheet. It's going to be due Tuesday when you come back to school. Have a great long weekend. I don't really care who wins the Super Bowl. You guys probably do. So go Chiefs. How about that? Talk to you later.